You spend 2 years getting genuinely comfortable with React. New job, week 1. The codebase is Vue. Different file extensions, different syntax, a different community telling you you're doing it wrong. By day 3, you're not lost anymore. Not because you crammed Vue's entire documentation over a weekend. You didn't. So what actually carried over? 10 mechanisms and every framework people argue about online, React, Vue, Svelte, Angular, Solid, is really just a different opinion on the same 10 answers. Learn these once, and every framework after your first one gets dramatically faster to pick up, because you're not learning new concepts anymore. You're just learning new spellings for concepts you already know. Every framework needs to answer one foundational question. When data changes, how does the framework even know? 2 real answers exist. Some frameworks, React among them, don't automatically know anything. They wait for you to explicitly say something changed, then recheck everything downstream. Others, Vue, Svelte, Solid, wire up actual tracking underneath your variables, so the instant you touch one, the framework already knows exactly what depends on it, no rechecking required. Same problem, 2 completely different answers, and picking which one a framework uses tells you almost everything else about how it behaves. Picture a counter on screen. In the first model, clicking increment doesn't update anything by itself. It just changes a plain number sitting in memory, and the framework has no idea that number matters until the next re-render sweep comes through and notices the difference. In the second model, that number was never plain to begin with. The moment you declared it, the framework wrapped it in tracking, so the click itself immediately and directly triggers exactly the one place on screen that reads it. Neither model is a workaround for the other. They're genuinely 2 different bets on where the bookkeeping should live. The real browser DOM is slow to touch directly, so several frameworks keep a lightweight copy of it in memory, a virtual DOM, and when something changes, they build a new copy and compare it against the old one. That comparison is called diffing, and the output is the smallest possible list of real changes needed to make the actual page match. Not every framework does this. The reactivity systems from Chapter 1 that already know exactly what changed don't need to diff anything. They just update that exact spot directly. Virtual DOM diffing is a solution to not knowing what changed. If you already know, you skip the whole step. This is also exactly why every list you render needs a stable key attached to each item. Without one, the diffing algorithm has no way to tell this item moved apart from this item was deleted and a different one was inserted in its place. And it'll guess wrong constantly, silently re-rendering, or worse, silently reusing the wrong internal state for the wrong row. The key isn't bureaucratic ceremony. It's the one piece of information the diffing algorithm has no way to infer on its own. Every component you'll ever write goes through the same 3-act structure regardless of framework. It mounts, appearing in the page for the first time. It updates, some number of times, whenever its data changes. And it unmounts, disappearing and hopefully, cleaning up after itself. Every framework exposes hooks into these 3 moments. Different names, component did mount versus on mounted versus a plain effect. But the same 3 moments every time, because a component genuinely only has 3 things that can happen to it. Data flows one direction, down, from parent components into children, as props. Change requests flow the opposite direction, up, from children back to parents, as events. A child never reaches up and directly edits its parents' data. It asks, the same way a form field doesn't set your bank balance directly, it submits a request. This one rule is why large apps built on these frameworks stay debuggable at all. When something's wrong, you can trace the data's path down and the event's path up, instead of chasing edits happening from every direction at once. Picture debugging a number on screen that's just wrong. In a codebase that respects unidirectional flow, there's exactly one place that number could have been set. Trace it straight up the component tree, no detours. In a codebase where components reach sideways and mutate each other directly, that same bug could be coming from literally anywhere that holds a reference to it, and just add a console log stops being a real debugging strategy once you don't even know which of 40 components to put it in. A regular website changing pages means a full reload, blank white flash, everything rebuilt from scratch. Client-side routing intercepts that click before the browser gets to it, swaps out just the piece of the page that needs to change, and quietly updates the URL bar to match, using a browser API built exactly for this. The History API, the same mechanism that lets the back button work correctly even though no real page ever loaded. The page never actually reloads. That's the entire trick behind every app that feels instant when you click between sections. There's no round trip to a server for a whole new page, just a swap of components already sitting in memory. Shipping your entire application as one JavaScript file means every visitor downloads code for pages they may never open. Code splitting breaks the app into chunks along natural boundaries, usually by route, so a visitor downloads the checkout page's code only if they actually go to checkout. Every major framework's build tooling supports this, usually through a dynamic import that looks like a normal function call but secretly tells the bundler, make this its own separate file, and only fetch it when this code path actually runs. Normally, your browser downloads a nearly blank HTML page. Then JavaScript builds the entire interface after the fact, meaning search engines and slow connections briefly see nothing at all. Server-side rendering runs your components on the server first, sends back a fully formed page of real HTML, and lets the visitor see actual content before a single line of your JavaScript is even downloaded. Same components, same framework, the only difference is where they first run. Search engines matter here more than people expect. A crawler that shows up to an empty HTML shell and has to fully execute your JavaScript just to find out what's actually on the page behaves very differently than one that gets real content immediately. And on a slow connection, a visitor staring at a blank white screen for even 2 extra seconds is a visitor who's already reaching for the back button, no interactivity required to lose them. That server-rendered HTML looks complete, but it's inert. None of the buttons do anything yet, because no JavaScript has attached itself to it. Hydration is the framework quietly walking through that existing HTML, attaching all the event listeners and internal state the interactive version needs, without throwing away and rebuilding what the server already sent. Done well, you can't see it happen. Done badly, that's the flash you sometimes catch where a page looks finished half a second before it actually starts responding to clicks. There's a specific well-known failure mode here worth naming, a hydration mismatch, where the HTML the server sent doesn't actually match what the client-side code would have rendered on its own, a date formatted differently, a random ID generated fresh on each run, content that depends on something only the browser knows. When that happens, the framework has to notice the mismatch and quietly throw away and rebuild the broken piece, right there in front of the visitor, which is slower than if you'd never server-rendered that piece at all. Here's where this stops being a list of nice features and starts being the actual architecture of every app you'll ever build with one of these frameworks, because the next 2 concepts aren't optional extras. They're the ones deciding whether your whole codebase holds together as it grows. Passing a piece of data from a top-level component down through 6 layers of children that don't even use it, just so the 7th layer can finally read it, is called prop drilling, and everyone who's done it has hated it. Every major framework has an escape hatch, context in React, provides /inject in Vue, dependency injection in Angular, that lets a component reach up and grab a value directly from an ancestor, skipping every layer in between. Different name, same job, get data to the one component that actually needs it, without forcing everyone in between to carry it. The theme of your entire application is the textbook case. Every single component might theoretically care whether it's rendering in light or dark mode, but hand-carrying that value explicitly through every layer of a real app would mean touching hundreds of components just to add one visual setting. Set it once, high up, with context or its equivalent, and any component anywhere underneath can just reach up and read it directly, whether it's 1 layer down or 20. Nothing you write in JSX or a Vue template is valid JavaScript on its own. The browser has never once executed raw JSX. A compiler step, running before your code ever reaches a browser, transforms that friendly template syntax into plain function calls that build up the actual component tree. This is the exact same lexical analysis to code generation pipeline covered start to finish in the compiler's video on this channel, just pointed at your component templates instead of an entire programming language. Write a single line like a div containing a greeting, and by the time it reaches the browser it's already been rewritten into a plain function call constructing that same structure. The tags and curly braces were only ever there for you to read, never something any browser engine has to understand natively. Here's what none of these 10 mechanisms actually promise you, and it's the part every framework's marketing page conveniently leaves out. Every one of these 10 solves a real problem, but every one of them also adds a layer between what you wrote and what actually runs, and that layer has its own cost. Reactivity tracking has real memory overhead per tracked value. Virtual DOM diffing burns CPU cycles comparing trees, even when nothing meaningfully changed. Hydration alone is a big enough performance problem that entire new frameworks exist specifically to avoid it. None of these mechanisms are free, they're all trades, accepting some fixed overhead in exchange for not having to handwrite direct DOM manipulation yourself. And the framework handles it, is doing a lot of quiet, expensive work every single time you read that sentence. So the next time you pick up a framework you've never touched, Don't start with the syntax. Start by answering 5 questions about it, in order. 1. How does it know when something changed? Tracking or diffing? 2. What actually happens at each of the 3 lifecycle moments? And which of your bugs came from getting that order wrong? 3. How does it move data down and events back up? And where does that rule get broken first in a codebase under deadline pressure? 4. Does it render first on the server or only in the browser? And what does that mean for the first thing a visitor actually sees? 5. What does its compiler step actually transform your code into, underneath the syntax you're staring at? Answer those 5 in that order, and the framework's entire syntax turns into documentation you're skimming for spelling. Not 10 new concepts you're learning from zero. That's the real difference between a developer who knows React and one who understands what a front-end framework actually is. The first one has memorized one dialect. The second one has learned the 10 questions every framework in this space is quietly answering one way or another, and can walk into any of them, React, Vue, Svelte, Angular, whatever gets invented next year claiming to be different, and start reading its source instead of its marketing. The syntax was never really the hard part. It just felt that way the first time, because nobody had told you the 10 questions yet. If you want to see where idea 10 actually comes from, a full compiler pipeline, not just the one step pointed at your templates, go watch Compilers, From Code to Binary on this channel next.